In this video, we're going to discuss the product, quotient, and power rules for logarithms. In particular, we're going to develop the product, quotient, and power rules from logarithms using the corresponding rules for exponents. And we're going to use these rules to expand very simple logarithmic expressions. The first rule we're going to discuss is often called the product rule. It states that the log base b of a product, which we're representing as m times n here, is going to be the log base b of m plus the log base b of n. In other words, the log of a product is the sum of the logs of the individual factors. This is an analogous statement to the standard product rule for exponents, which says that x to the a power times x to the b power is equal to x to the a plus b power. Here, the rule for exponents turns a multiplication problem, x to the a times x to the b, into an addition problem, x to the a plus b. The logarithm property undoes this. It's actually pretty straightforward to see why the product rule for logarithms follows from the product rule for exponents. If we set m to be the log base b of capital M, so that's lowercase m to be the log base b of capital M, and lowercase n to be the log base b of capital N, then we can see that b to the lowercase m is equal to capital M, and b raised to the lowercase n is equal to capital N. So this is translating both of these logarithmic forms to their corresponding exponential forms. Right? And now we can compute the log base b of m times n. We can substitute in the values for capital M and capital M that we just obtained. So that's b to the m and b to the n. So we're just substituting in our values for m and n. Now using the product rule for exponents inside the logarithm, this is log base b of b to the m plus n power. And now we have a log base b of b raised to a power. And as we've previously seen, this is just the value of that exponent. So we can just get m plus n here. And of course, going back to what lowercase m and lowercase n represent, lowercase m is the log base b of capital M, and lowercase n is the log base b of capital N. And now comparing the first and last terms in this chain of equations, we see that we get exactly the product rule mentioned at the top of the screen. For a quick example where we have to use the product rule for logarithms, let's look at this one. In this case, we're asked to expand the expression log base 3 of 30 times x times 3x plus 4. So in this term, notice that we have three quantities being multiplied together: the number 30, the variable x, and the expression 3x plus 4. And so this is log base 3 of a product of three things. The product rule that we just talked about can be extended to any number of terms in the obvious way. We just simply add the logarithm of each individual factor. And so if we want to expand this, we're simply going to write log base 3 of each of our factors. So log base 3 of 30, log base 3 of x, and log base 3 of 3x plus 4. And the product rule says to add these together. And so this expression here, log base 3 of 30 plus log base 3 of x plus log base 3 of 3x plus 4 is exactly the same as the log base 3 of 30x times 3x plus 4. Notice that there is no rule for simplifying the log of a sum. And so this log of 3x plus 4 is just something we have to leave alone. There's no nice way of being able to break that logarithm up. And so this term at the end is as simple as it can be. The second property that we're going to look at here is called the quotient rule. And it's called that because we're looking at rewriting log base b of a quotient m divided by n. The quotient rule says that that expression is equal to the log base b of m minus the log base b of n. This is analogous to the exponential quotient rule, which says that b to the m power divided by b to the n power is equal to b to the m minus n power. Just like the product rule, we can pretty quickly deduce the quotient rule for logarithms from the quotient rule of exponents. Just like in that previous case, we're going to let lowercase m be the log base b of capital M, and lowercase n be the log base b of capital N. And we're going to start by trying to compute the log base b of capital M divided by capital N. We will substitute in the appropriate values. Capital M will be b to the m, lowercase m. This is the analogous fact, the exponential form of m equals log base b of m. Capital N will be lowercase b to the lowercase n. Again, we're converting n equals log base b of capital N to exponential form, just like we did with the product rule. This is the log base b of b to the m minus n. And again, we have log base b of b to a power. This results in just that power, m minus n. And m and n are, as defined earlier, log base b of m and log base b of n. And they're being subtracted. So we get the quotient rule, again, following from the quotient rule from exponents. So for an example, using the quotient rule, let's expand the log base 2 of the expression 15x times x minus 1, all divided by the product of 3x plus 4 and 2 minus x. So first we see that we do have a log base 2 of a quotient. And so the first thing that we do need to do is use the quotient rule to break this up. And it'll be the log base 2 of our numerator, 15x times x minus 1, minus log base 2 of our denominator, 3x plus 4 times 2 minus x. Now each of these logs can be expanded further. Each of them are products of 2 or more terms, and so we can use the product rule to expand both of these resulting logs here. For our first one, we see we have 3 factors that were being multiplied together, so we can compute log base 2 of 15 plus log base 2 of x plus log base 2 of x minus 1. And all 3 of these logarithms are as simplified as possible. Log base 2 of x minus 1, for example, cannot be split apart. Now we're going to subtract log base 2 of 3x plus 4 times 2 minus x. So here we can use the product rule again to rewrite that as the log base 2 of 3x plus 4 plus the log base 2 of 2 minus x. Now notice I put that entire expression in brackets, and the entire expression is being subtracted. And that's because we're subtracting this whole term, log base 2 of that product. And so in order to include that, or in order to count that correctly, we do need to subtract both of the terms that we get from the product rule. And so rearranging this in a natural way, we get the log base 2 of 15 plus the log base 2 of x plus the log base 2 of x minus 1 minus the log base 2 of 3x plus 4 minus log base 2 of 2 minus x. This last negative sign might be the one that is most commonly missed. And again, it's coming from that distribution of the negative sign that is introduced with the quotient rule. A third important rule of logarithms is called the power rule, stated here. It says that the log base b of m to the nth power is equal to n times log base b of m. Essentially what is happening is that the exponent of n inside the logarithm is being moved outside the log, but instead of as an exponent, as a coefficient. This allows us to compute log base b of m of a simpler expression m, and just multiply by n after the fact. In order to justify this, we would again go back and use properties of exponents that deals with powers like this, but for purposes of time, that justification is omitted. So we'll take a look at a couple examples involving the power rule. First, let's expand log base 2 of x to the fifth. This is about as simple as it can get in terms of the power rule. We have inside the logarithm this expression x to the fifth with an exponent of 5. The power rule says that we can bring that 5 down in front, and that this is going to be equal to 5 times the log base 2 of x. And so this is equivalent to the expression that we're given, log base 2 of x to the fifth, but it is a little bit simpler. Here we just have to compute log base 2 of x and then multiply by 5. And multiplying by 5 is typically a lot easier than raising a number to the fifth power. Okay, here's another example where we're asked to expand log base 3 of 25. Might be unclear what we're supposed to expand here, but notice that we do know that log base 3 of 25 will be the log base 3 of 5 squared, since 25 is 5 squared. And now that exponent inside the logarithm can be brought down in front, and this can be written as 2 times the log base 3 of 5. And finding a logarithm of a number 5 is a lot simpler than finding the log of 25. Of course, these numbers are still not very big, but if you can imagine examples where instead of 25, we might have a number that is quite large, where finding a logarithm is incredibly challenging, whereas finding the log base 3 of 5 is quite easy for any calculator to do.